So, hello everybody. My name is Ricardo Castro. I come from University of California, Merced, and today I would like to talk about multi-layer control for hybrid balancing systems. And before starting my talk, I would like to acknowledge the contributions of my colleagues, Albert Pereira, Gustavo Zaraújo from Port University, Jorge Barreras from the Imperial College of London, and Herschel Pangborn from Penn State. So my talk is going to be divided in three parts. So at the beginning, I'm going to introduce you to the hybrid balancing concept and why it's an interesting idea to work with this kind of systems. Then in the second part, I'm going to talk about the design of the control algorithm, which relies on a multi-layer model predictive control framework. And then in the last part of my talk, I'm going to show experimental results that we obtained with this controller in a small scale laboratory prototype. The motivation for this work is electric vehicles. So due to voltage and power requirements, we often need to stack several cells in series. And this series arrangement poses several challenges for the operation of the battery. One of the challenges deals with the non-uniform aging of the cells. And to better understand this issue, I plot here in this slide the capacity of a battery pack over the charge-discharge cycles. And so we can see that at the beginning of life, all cells they have high capacity and small variation. But then as we go through the cycles, the capacity drops. And then you start to see that some cells, they age faster than the others. And this end up introducing also variations, significant variations from one cell to the other. And so these non-uniform features and properties of the cells limit the performance, energy, power that we can extract from the entire battery pack. And so to mitigate this problem, there are several approaches that we can follow. One approach relies on passive balancing. Here we connect a resistor with a switch to the cell, and then we dissipate energy from the cells with a higher charge in order to equalize the pack. It's simple and low cost, widely used in the industry, but it's not very energy efficient. A more attractive approach relies on active balancing, using power electronics to shift energy from one cell to the other. It's a bit more complex, more costly, but offers much higher energy efficiency. And in the last years, researchers, they realized that we can do more than just charge equalization with the balancing hardware. So there's been some research on also performing thermal equalization of the battery pack using balancing hardware. And depending on the structure of the power electronics, we can also adapt the output voltage of the battery pack. And in our case, what we've been doing is to exploit the balancing hardware to also enable hybridization of the supercaps. And that's the main, let's say, research stream that we'd like to talk about today. Hybrid balancing has two main ideas. One revolves around the use of multiple energy storage devices, in particular supercaps and batteries. Supercaps, they offer high power density, but they have limited energy density, while batteries usually have complementary characteristics. So higher energy density, but not the same peak power capability. So there is the interest of combining these storage devices in order to exploit the best features that they have to offer. The other idea is related with the use of the balancing hardware to perform equalization and at the same time hybridization of the supercaps. So especially using cell-to-cell balancing hardware, we can easily find electrical interfaces to incorporate supercaps. And so this way we can use a single system to perform these two tasks and making them more attractive for practical implementations and reducing costs. And that was the main motivation for the use of this hybrid balancing concept. But for today, I'd like to talk more about the control algorithm that we designed for this system. And particularly, we are interested in finding the balancing currents that we extract from each battery cell in order to fulfill several goals and objectives. One of the objectives is related with the balancing of state of charge. So we want all the SOCs to be equal. And to achieve that, we can easily formulate the quadratic cost. Likewise, we also want to minimize imbalances in the temperature of the battery pack. So we can also easily formulate cost to penalize these imbalances. We do not want to waste energy, so we also want to minimize losses in the battery, the supercaps, and also in the balancing hardware. And very important is the aging of the battery cells. And we want to minimize battery degradation, and particularly capacity fade. But battery aging is a tricky topic, very complex. And in our work, we adopted a more pragmatic approach. And we realized that in many of the aging models, the current has an important impact in the capacity drop. Especially if we are able to decrease the current, often we see a slower capacity drop in the battery. And so using these insights, we penalize current as a proxy for capacity fade. Additionally, we also need to fulfill limits for the currents that we can extract with the balancing hardware, also physical limits in the SOC of the storage elements, and we also have dynamics for the temperature, power balance constraints between the storage device, the load, and this problem needs multiple control inputs, also deals with multiple objectives, multiple constraints. And so MPC is a very attractive technique to deal with these challenges. And as a result, it was the technique that we employed. So when it comes to the design of the MPC, we started first with a single layer MPC that attempts to solve this challenging problem in a single layer. And so we can easily formulate the cost function that groups all the cost terms that I introduced in the previous slide with appropriate weights. We can also build the prediction model for the SOC of each battery model, for the temperature dynamics of each battery model. We also have an algebraic constraint that results from the power balance between the supercaps, batteries, and loads. And of course, we have initial states and also some exogenous inputs for the prediction, such as the environmental temperature and also the output power that is being requested to the battery. And one of the most important parameters for the performance of this algorithm is the prediction horizon, this upper end. We realized that for balancing purposes, for SOC balancing, temperature balancing, we can achieve high performance using a short prediction horizon. So a few seconds is enough to optimize these costs. But when it comes to battery stress minimization and loss minimization, we often need to use longer prediction horizons to optimize these costs. But this introduces a problem, which is the increase of computation time. So as we raise the prediction horizon, the average CPU times, they grow significantly, and then it's difficult to fulfill real-time computation constraints for this single layer MPC. And so motivated by this problem, we decided to formulate a multi-layered MPC. So we realized that for optimizing the stress, battery stress and energy losses, we can reduce the complexity of the prediction model. So we can use a pack level prediction model that neglects cell-to-cell variations and treats the battery pack as an ideal single cell. And so this way we can reduce the number of states and control inputs that we have in the prediction model. And this allows us to increase the prediction horizon, and this helps optimizing these stress and loss costs. And then when it comes to the equalization of charge and temperature, we do this at the lower level with a higher model complexity using a model level prediction. And to reduce the computational times, we are able to operate shorter prediction horizons. And so by playing with the model complexity and prediction horizon, we are able to reduce the computational time, as you will see in the next slide. Additionally, I would also like to stress that the information that we exchange between these two layers is a reference for the state of charge of the supercaps, which we then augment or bring as an additional cost for this low-level MPC. When it comes to the performance of the single layer versus multi-layer MPC, we observe that the performance is very similar for balancing tasks, for stress, and more importantly, when it comes to the average computational time, we saw that with the multi-layer MPC, we can significantly decrease the CPU time as we raise the prediction horizon. And so we obtain similar performance, but with lower computational time, and this is very attractive for real-time implementation, which we did in a small-scale laboratory prototype. So we built a small battery pack with 10 cells, which were divided in three models. Model 1 with 4 cells, Model 2, Model 3 with 3 cells. And this arrangement intends to emulate capacity imbalances that might appear as the battery pack ages. For the balancing, we employ a dual half-bridge topology that provides galvanic isolation and also bidirectional power flow. And to compute the MPC solution, we employ the Raspberry Pi 3 as an embedded control unit. So let me show now some experimental results that we obtained with this prototype. So here on the left side, you can see the results of a single layer MPC. In this control unit, we were only able to use a prediction horizon of 10 seconds with a single layer MPC due to the computational constraints. And so here you see the balancing signals that we obtained, the state of charge of the battery models, the temperature increase, and also the state of charge of the supercaps. And it is interesting to see when you look at the state of charge of the supercaps that the single layer, which is such a short prediction horizon, results in greedy energy management strategies. So you see we discharge the supercaps very quickly during the first phase of the driving cycle. And then in the second phase, the supercaps are not able to support the battery. And as a result, you see a significant increase in temperature in the battery models. On the other hand, we have the multi-layer control. With multi-layer, we were able to significantly increase the prediction horizon for the high-level MPC. And this brings several advantages. So especially when it comes to the temperature, we see that the maximum temperature decreases in 1 degree. And this is the result of a better management of the supercaps energy. So you see that with a multi-layer and longer prediction horizons, we don't discharge the supercaps so quickly. So we hold it and we deploy the supercaps in the second part of the driving cycle. And this provides a more effective support for the battery models and justifies this decrease in maximum temperature that we observe in the battery models. We also observe that with the multi-layer MPC, we were able to decrease the battery stress in the models in up to 15%. And in comparison with the single layer, we also decreased the capacity fade in up to 3.7%. And this brings me to the conclusion of my talk. So we introduce you to hybrid balancing, which performs equalization and hybridization in the same system. I also introduce you to the multi-layer MPC framework to command this system, which decompose the problem into 2 layers that operates with different model complexities and different prediction horizons. And then we validate these in a small scale prototype, and we show benefits of the multi-layer MPC in several performance metrics. And in future work, we would like to validate these concept in large battery packs and also investigate the potential of this technology in battery second life applications. And that's the end of my talk. So thank you very much for your time and attention. I'm looking forward to questions.